Hello everyone, this is Professor Jeff Wilkerson, Professor of Physics at Luther College, with an introduction to the experiment we're going to do September 14th and September 21st in Modern Physics 1, Physics 281 here at Luther College. What we're going to do is we're going to measure the charge to mass ratio of the electron, much as J.J. Thomson did, but we're going to do this, and we're going to ask the question, to what precision would we need to make these measurements so that relativity was an important part of the work that we're doing? So we're going to be doing some relativistic calculations all the way along, and we're going to try to improve the precision as best we can, and think about the difference between precision and accuracy and the systematic effects that might be coming in here. This is our apparatus that you see here. So there's an electron tube, and electrons are boiled off down here, and we provide a bit of accelerating voltage for them to give them kinetic energy as they fire through a hole in the plate right there. There's a grid to help shape the beam. We want to make a nice narrow tight beam. Just enough air left in this tube that you see a blue glow from the electron beam as it goes through there. These coils, there's coils right here, and these coils of wire will run a current through with this power supply, and this power supply then will provide a magnetic field, provide a current that provides a magnetic field, and will bend those electrons in a semicircle, we'll see, and we have circles on that disk of various diameters, radii marked, and so you'll see the beam when it hits those, we'll see them glow. Your job is to think a lot about where it's centered on that ring, so you try to minimize error and uncertainty, both by centering it on that ring, and then to think about the systematics that are going on. Suppose there are stray magnetic fields in this lab. Suppose they're aligned with the magnetic field you're producing here. Suppose they're anti-aligned with the magnetic field. Suppose they're perpendicular magnetic. What are you going to do to try to correct for that? What experimentally can you do? So think that through and try to figure out how you are going to do this experiment to try to minimize those effects, to do the best you can. This is a deceptively simple experiment. Pretty easy to bend those electrons in a ring, in a circle, semicircle, and have them hit these rings as they move in there, and to calculate what the charge to mass ratio for the electron needs to be. But there are a lot of little different things that we need to do, and relativity is just one of those things that we ask about. We only ask about that right now because that's what we're talking about. And so we want to start thinking about, as we do experiments, asking the question, where would relativity start to come into play, and under what conditions here? So what we're going to do, this power supply provides the current to these rings to provide the magnetic field that runs through there. This power supply over here, this is providing a voltage that heats up the electron generator there, provides the electrons. This is your grid power supply, your grid voltage, and this is the voltage for the plate. It says right there it's important that the plate voltage be limited to 200 volts max, even though this knob can allow you to turn that up to much more, up all the way up to 1,000 volts. So you need to figure out, be very careful not to turn that above 200 volts, and in fact, this knob is highly sensitive. You're reading that voltage on here. Make sure that this is set to 200 volts so that it would peg out if you go past it, and turn that knob very slowly. This is your grid voltage. You adjust that voltage to get a nice, fine, tight beam. And so what we're going to do is make sure all these knobs are turned to the left, and we're going to turn that thing on. We're going to allow that to sit there for a little while. I'm going to get it move around so the lights don't go off again. We're going to allow that thing to sit there for a little while, and as it does so, then we're warming up the electron supply there. We're going to start to get those electrons off. I'm going to turn this voltmeter, this DVM, the digital multimeter, on with that knob right there. Okay, and So we're going to see what we can do to try. We're going to turn that voltage up just a little bit, that potential up, keeping it, being very careful to make sure that we don't go above 200 volts. And in fact, my guess from experience doing this before, you're going to get the best results if you keep the plate voltage within a range of about 80 to 120 volts. And so then we're going to start right there. And then we're going to try to adjust the grid voltage to see if we can see a beam right there. We've got a pretty good tight beam. My guess is you can't see it. I'm going to actually move the camera up closer here for a second to see if you can see that beam. Maybe you can see the beam in there. We'll turn the lights out in a second. It gets pretty dark, as you saw a second ago. And so perhaps you can see that beam that was there. I don't know. And so we're generating a pretty good beam through there, right? If we turn on this power supply, we'll turn it up, turn it on. We've got the voltage turned all the way down. That's your coarse voltage setting. That's your fine voltage setting. The current limit is turned all the way up. We want to be able to produce a pretty good current with that. So we've got this thing set up. Let's go ahead and zoom in here just a little bit so you can see what's going on there. So you can see this. I'm going to go shut the lights out so you have a little bit of a better chance to see what's happening there. I hope you can see that electron beam. It's a nice bright blue electron beam there. Oh yeah, looks good to me. You see the electron beam right there. Watch what happens. I'm going to play with the grid voltage and try to tighten that up and make that a nice tight beam. You see how it gets fuzzy and then tighter and then fuzzier? And so I'm going to pick right there in the middle there. I got a nice tight electron beam that comes out of there. And now what I'm going to do is start to turn up the current in the coil here that's making the magnetic field. Watch what happens to that beam as I do so. We definitely see good stuff going on. Hopefully you can see that beam curling around there. As I keep turning the current up, I curl it enough, I get the beam, it hits one of the rings. See the green glow when it hits the ring? Phosphorescence there, it's got that bright glow, so you can try to judge right when it's hitting the ring. And then I'm going to hit the next ring in and see if I can get a bright spot on it and see if I can get it all the way, if I have enough current to get it all the way down to the innermost ring. I do. You see that bright spot? Perhaps you can see the bright spot. That is the glow of that electron beam on the innermost ring. Turn the current back down and you see the electron beam getting larger radius of curvature. Okay, so that's what we got going on here. And what we want to do, then I got a little light back on the situation. You're going to run through this several times. This is what we do, right? We did this in Physics 182 in the spring, where we make a lot of measurements and try to average those measurements where we can average those measurements and ask for inconsistencies from one set of measurements to another set of measurements. For example, do you get the same charge to mass ratio on the innermost ring as you do on the next ring out and on the next ring out? Are the rings consistent? But you're also going to tweak the magnetic field. Right? There's a setting that I have for current and potential for these coils that worked pretty well for this 84 volts of plate voltage right there. And I turn that. And so what I'm going to do is I'm going to try maybe that's so you can ask the question, what's the thing to do? Do you want to tweak the magnetic field current just a little bit and have a new magnetic field current and then tweak the plate voltage? That's a good way to do it. You have to be careful not to exceed the 200 volt limit here as you do that. Or do you want to keep this at this 84 volts like we just did and tweak the magnetic field and hit the different rings like that. And so you can have different accelerating voltages. You can have a fixed accelerating voltage with different magnetic fields. You can have a fixed magnetic field with different accelerating voltages. But we want to tweak one of these just a little bit at a time. So suppose we were to tweak this 84 volts up to 87 or 88 volts and then run through the whole thing again. And then tweak it up to 90 volts and 92 volts and 94 volts and run through the whole thing again. And we'll analyze this as a big data set, but also little pieces of data like we've grown accustomed to doing last semester, where we look at different pieces of the data and say, are the results when looked at this way consistent with the results when looked at this way? And think about how we want to approach this. So this is your setup. This is what you got. Hopefully you can see everything we were working through here. You get an idea of how to come into the lab next week and settle down and set right to measuring the charge to mass ratio and think about all the complications that go along with it. So that's what we got for you. Look forward to doing this experiment. I think it should be a lot of fun, a lot of different things to think about to make this work the best it can possibly work. Thanks everybody. We'll see you soon.